Hello folks and welcome to today's lecture. In this session, we will examine one of the key non-ideal characteristics of operational amplifiers, the open loop gain. While the ideal op-amp is often modeled with infinite open loop gain, this assumption does not hold in practical devices. This naturally leads us to two important questions. What is the true behavior of the open loop gain in real op-amps, and what mathematical model accurately describes it? Let us begin our discussion. As we know, the ideal operational amplifier is modeled with infinite open loop gain and infinite bandwidth. However, when we look at the datasheet of any practical op-amp, we immediately encounter a graph labeled open loop gain. For example, in the case of one of the most well-known op-amps, the LM741, the open loop gain curve resembles the response of a first-order system. From this observation, we can conclude that the open loop gain is frequency dependent. At low frequencies, the gain has a very high value, typically around 116 decibels, but once it reaches the corner frequency, the gain begins to decrease at a predictable rate. In other words, the amplifier's gain is not constant across all frequencies, which is consistent with the behavior of any real-world electrical system. We may now ask, why does the open loop gain curve resembles a first-order system? This characteristic is deliberately designed and serves a very important purpose. In any electrical system, unavoidable stray capacitances can introduce additional poles, which may cause instability and degrade the system's performance. To counteract these effects, op-amp designers add internal compensation capacitor. This capacitor forces the amplifier to exhibit a first-order response over a wide frequency range. This is why we say the op-amp is internally compensated. By placing the cutoff frequency created by this compensation capacitor at a very low frequency, well below the frequencies at which unwanted poles could cause instability, the designer ensures that this pole becomes the dominant pole of the system. As a result, it effectively controls the overall transfer function and guarantees stable operation when the op-amp is used with feedback. Starting from the compensation capacitor's cutoff frequency, the open loop gain begins to decrease at a rate of 20 decibels per decade, which is the characteristic slope of first-order system. Therefore, we can model the open loop gain using the following expression, where A sub O is the low frequency or the DC open loop gain, and omega C is the cutoff frequency or the dominant pole frequency introduced by the internal compensation capacitor. This equation accurately describes how the open loop gain varies with frequency in a real internally compensated operational amplifier. To summarize the key points discussed in this lecture, we have 1. The open loop gain of a real operational amplifier is not infinite, unlike the ideal model. 2. The amplifier's gain is frequency dependent. As frequency increases, the open loop gain decreases following a predictable slope. 3. The open loop response is dominant by a single pole. This dominant pole is intentionally introduced through internal compensation to ensure stability and reliable operation. So, understanding these non-ideal characteristics is essential for designing stable and accurate analog circuits. Thank you for watching. If you found this video useful, feel free to like, share and subscribe to the channel to support this type of content. Stay creative, stay passionate, and I see you in the next video.